Okay, this video is to get you started on the Vivado software. So we're going to use this logic circuit as an example. Okay, this logic circuit here of 3 gates along with this truth table. So we'll be modeling this logic circuit and then seeing if we get this corresponding truth table. So once you open up Vivado, you should get a screen that looks like this, and we want to create a project. Okay, so a wizard will appear. Just click next. Okay, so name your project. Use something descriptive. I'm going to use first logic circuit. And I'm going to put this in. Let's see my revamp folder. Okay, so name your project and put where you're going to put it. Okay, we want an RTL project, so just hit next here. Alright, now in this window you can either add or create files. So if you had like a previous project that you wanted to get a file from, you could by just hitting this button, add files. We're going to add a constraints file coming up, but here for a design source, which is the actual file that's going to model that logic circuit, we want to create the file. And we're using system Verilog, so make sure you choose system Verilog. And I'm just going to abbreviate first logic circuit with FLC. Okay, so we're done with that. Okay, so here we're going to add this constraints file. You'll see what the purpose of the constraints is later, but we have a template for that file. So add files, and let's see, I gotta go find it. Yeah, so yeah, I got 3 here. They're basically the same, but this is the one we want. Okay. Alright, here we put in the board that we're using. So on your basis 3 board, or excuse me, on your basis 3 box that the board came in, on the back of it there is this model number. It's XC7 A35 TICP. Okay, and then once you put in that, you only have one choice. Okay, and it's this one right here. Make sure you have the right one. Okay, if you choose the wrong one, then when you go to implement your design on the board, it's not going to work because the pin numbers aren't going to match up. So it's important that you choose the right one. Okay, so we finish. Alright, so now we're going to put in the inputs and outputs of our circuit. So you can see on this diagram that the inputs are labeled A, B, C, and the output Q. I'm going to be a little bit more descriptive than that. The reason you want to be a little bit more descriptive is especially when you have circuits that have a lot of different gates, and like you'll have like a big circuit made out of little circuits, and sometimes like your smaller circuits will have the same inputs like A, B, C, but you want to distinguish one circuit from another, so it's good to have more descriptive names for your inputs and outputs. So what I'm going to do here is, instead of just saying A input, I'm going to have it as FLC underscore A input. It's the A input of our first logic circuit. Yeah, here is where you get to choose input, output, or in, out. We're never going to use in, out. It's either an in or an out. This is an in. And this is a single bit input. If you had an input that had more than one bit, and we'll get to inputs like that later on in the course, you would choose this bus box, and then over here you could choose, like say you had an input that was 4 bits. Well, if you chose 3 here, that means you would have bits 3, 2, 1, 0, so 4 bits. Okay, but we don't have a bus here, so we don't have to worry about that. Alright, I'll call this FLC underscore B, and this is FLC underscore C. Alright, so those are our inputs. Then we have an output FLC underscore Q, and this is an output. Okay, so we got our 3 inputs, our 3 outputs. Alright, so I'm going to close this properties window. This window here, this is where our sources are. This is the FLC design source that we just created. So if I double click that, here's the code. Here's our constraints file that we added. And then we haven't added or created a simulation source yet, but we will coming up. But right now we're going to work on this design source. This is the Verilog code that's going to model that 3-gate circuit. And you can see there's a title block up at the top, so you can put in, you know, Cal Poly for the company, and then put your name. It has the creation date. It puts in the model name right here. Let's see, the only other thing I really do is I put a little description. So this is our first logic circuit. Oops. You know, Vivado. Like a Vivado test run. And again, purpose of the video is just to get you started on Vivado. We're just using this as an example. Okay, so down here, this is where your Verilog code is actually at. And you can see it put the model name, FLC. You always end with an end module. And then you can see here, it put our inputs and our outputs. And then after this semicolon and before the end module, that's where the Verilog code goes that's going to model the hardware. So again, we're modeling this logic circuit where we have an AND gate that's ANDing B and C together, and a NOR gate that has A and B at its inputs, and then these 2 outputs of these 2 gates is being ORed by this OR gate, and that's what our resulting output Q is. So in Verilog, a way to model this logic circuit is to use an assign. So you just assign the output to a Boolean expression that represents that logic circuit. So it's FLC underscore Q, that's what we declared our output to be. And then that's going to be B and C ANDed together. So LC underscore B ANDed, and in Verilog, AND is the ampersand symbol. So that's the symbol above 7 on your keyboard. Okay, so that's FLC underscore B ANDed with FLC underscore C. Okay, so that's taking care of, oh, and I need the parentheses over here. So that's taking care of the AND gate. And then the output of that AND gate is going to be ORed with the output of the NOR gate. Now the OR symbol in Verilog is the vertical line. Okay, so that's OR. And then we're going to have, let's see, A and B are ORed together, then inverted. So first, to do the A and B ORed together, it's FLC underscore A ORed with FLC underscore B. Okay, so that's those 2 ORed together, and then they get inverted to make a NOR. And inversion, the not, and Verilog is the tilde. Okay, so this is not a dash. Okay, it might seem like it's a dash, but that's a tilde. Tilde is a little squiggly line. On your keyboard, it's the key to the left of the key that has 1 on it. Okay, so you got to do a shift and then hit the key to the left of 1, the 1 key. And then also we have to end this with a semicolon. Okay. Now, if you make a mistake, like say we didn't put the FLC here, we just had, like B. You see the red line that appears. Anytime you see a red line, that means that you have some sort of error. And sometimes it's not, like the error may not necessarily be on that same line. Like for example, if I got rid of this semicolon, the red line is down here on end module, but the error is actually right before it. So just know that when you get a red line, the error should be somewhere close to that red line, but it might not be on the red line itself. It might not be on that same line. Okay, so for this basic design, that's all we need. We just need this one expression that relates the output to the Boolean expression for the logic that's between that output and our inputs. Okay, so this is saved. So now the next thing that we're going to do is we're going to do a simulation file. So we have to add a simulation source. So you hit add sources, and you see when you add sources, it's either constraints, design. The design source, again, that's the file where you're actually modeling the hardware, what we just did in FLC. Okay, but then you also have a selection here for simulation sources. Okay, so we choose that, and we're going to create a simulation source. So use system Verilog. And what I like to do, and I strongly recommend you do the same thing, is I'll call my simulation source the same as the design source with an extension of TV that stands for test bench. Okay, so that way I know that this simulation file goes with the FLC. You'll see that very quickly in this class we're going to get to designs that have more than one design source. So when you have more than one design source, you'll be doing multiple simulations because you'll simulate each of those design sources. So if you use this technique of using the same name with the TV suffix, you'll know which simulation file goes with which design source. Okay, it just makes bookkeeping easier. Okay, so we're finished with that. Alright, now we're going to put in inputs and outputs to our simulation source. So here I'm going to use TB as the prefix, so TBA for input A, TB underscore B for input B, TB underscore C for input C. No, but you're going to see it really doesn't matter what I'm calling these inputs and outputs in just a second, but TB Q. Alright, so it's generating that sim file, or test bench sim file, same thing. Some people will use the prefix SIM for sim instead of TB for test bench. Doesn't matter. Alright, so now we're going to look at that sim file. So again, you have this title block, and we can do the same thing here. Cal Poly, your name. With the sim file, since I know that this sim file goes with FLC, I don't put a description, because in the name I know what it's for. Okay, so here, just to save some time, Well, first of all, you can see that it put the inputs and outputs between these two parentheses after the module name. And then again, you have an end module that's always the last line in the Verilog code. Just to save some time, I previously did the simulation, so I'm just going to do a copy and paste here. I'm going to go to what I did earlier. And again, I'm just doing this to save some time, and then I'll point out, you know, what I had to edit to get this. Okay, so we're just going to take this. You know, you would actually have to type this in. I'm just going to paste it in here. Oops, what did I do? Oh, I'm just going to copy over this, hopefully. Yeah, looks like a copy right. Okay, but you can see here that in my previous, I called it sim instead of test bench, so I got to change that. Let me put that to TV. Okay, so you got your module name, right? Same as the design source with the TV suffix. Excuse me. Now, what had to be changed here is, and this is why it didn't really matter what we called A, B, and C, and Q when we were creating the sim file, because in a sim file you don't have inputs and outputs. Okay, you use this logic, okay, which basically means like some signal. Okay, it could either be an input or an output. So, you know, that had to be changed. And then also you have a semicolon after these logic excuse me, these logic declarations. Alright, so after you have this part of the code, the next thing is you put the name of the design source that you're going to simulate. So since we're going to simulate this design source FLC, that's why I put FLC there, then that's followed with UUT. UUT stands for Unit Under Test. So we're using this simulation file to test this design source. And after the UUT, inside parentheses, you have the following, where this code is connecting the inputs and outputs of the design source that's going to be under test to the simulation inputs and outputs. So this part of the code right here, this dot FLC underscore A, and then in parentheses TB underscore A, what that part of the code is doing is that it's taking this input of our design source, right, of the circuitry that we want to test, and it's connecting it to the input A of the test bench. Okay, likewise, this part of the code right here, it's taking the B input of the FLC, what we want to test, and connecting it to the test bench B input. Alright, and same thing here with the C input, and then same thing over here with the Q output. Okay, after this line of code, now comes the test cases. Now, in Verilog, System Verilog, a comment, if you want to make a comment, you start it with this double dashes. And then you put always begin, and an always begin always has to have an end. Okay, so the end module is what ends the module, and that's always the last line in the code. And then anytime you have a begin, like this begin after the always, you also have to have a matching end. And then in between the begin and the end, these are our test cases. So we're testing this logic circuit that has 3 inputs, right? We're going to verify that it's going to give us this table, and if you have 3 binary inputs, the number of different combinations that you can have is 2 to the number of those inputs. So since we have 3 inputs, 2 to the 3 is 8. Alright, so you see we have 8 possible combinations of zeros and ones at our input. You see, one way to look at this is if you just look at this as binary numbers, this is counting from 0 to 7. Right, with 3 bits, you can represent 0 to 7 in binary. And you see these are in order if you think of binary numbers, 0, 1, 2, 3, 4, 5, 6, 7. So that means to thoroughly test this logic circuit, we need 8 test cases. And that's what we have here. See, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then all ones. And the way you represent a single bit is with this one tick mark B. You know, if you had more than one bit, like say you had a 4-bit input, you would have 4 tick mark B followed by, you know, the 4 bits, whatever they were equal to. Now the hash mark 10, the number sign 10, that represents a delay of 10 nanoseconds. And the reason we use 10 nanoseconds is because on the basis board, the frequency of the clock signal, which is basically how fast the board operates, is 100 megahertz. And the period of a 100 megahertz signal is 10 nanoseconds. So we're doing a test case for every clock pulse of the clock that's on the basis board. At least that's what the simulation is simulating. Okay? So you can see that I have a delay of 10 nanoseconds at the start and then between each of the test cases. That's so the test cases don't overlap each other. Alright, so I think we're ready to go ahead and simulate. So you come over here to run the simulation. Okay, so it's going to run the simulation now. Oh, and actually I made a mistake here. It's probably going to come up with some errors. I just realized I forgot to do something. But that's okay. You guys get to see an error here in real time. Okay, great. You see what happened? This is the timing diagram. And when you get blue and red and you get Z's and X's, that means it's not right. When you get a good timing diagram, you'll see green. Okay, you'll see the color green. And the reason why we're getting a bad simulation here is because I forgot to do something. And what I forgot to do, although it just corrected itself here, it looks like. But when I ran this, when I started the simulation, it hadn't updated, I guess, where it didn't have this test bench as the top module. You see this pyramid symbol to the left of the file names? That indicates what your top module is. And before you do a simulation, whatever module you're simulating, both the design source and its corresponding test bench or simulation also have to be the top module. So, you know, when I first started the simulation, I noticed that the pyramid wasn't next to this, you know, this file here. So that's why I knew it was going to be an error. Now it corrected itself, but you can do it manually also. Usually it doesn't correct itself. The way you do it manually is you right click and then right here set as top. Now you can't set it as top because it's already the top. But if it wasn't the top, that's how you would do it. And same thing with the design source. If it's not the top, you just right click it and then choose it to be the top. Okay, but it should run correct now because it's got the simulation file as the top module. Okay, maybe we have to close this. Okay, so let's see if it's going to run now. Okay, there we go. So you see we got green. Now notice that it ran for 1,000 nanoseconds. okay, which is, you know, 1,000,000 picoseconds. Well, we only have 8 test cases, and they're separated by 10 nanoseconds. So we can run it for a lot shorter time. In fact, see up here, we got 100 nanoseconds. That's what I'm going to do next. I'm going to restart this simulation and just run it for the amount of time that we need. That way, you know, we don't have more of a timing diagram than what's necessary. So this was already set for 100, but if it wasn't, you could just set it to whatever number you wanted just by changing that number in the window. Okay, so first of all, to run it for this time, we got to restart it to begin with. So that's this button. So that's going to wipe out what was there. And then you just hit this button, and that will run it for the 100 nanoseconds, which again is 1,000 picoseconds. Next thing I'll do is I'll use this zoom to fit, and we get a good look at our signals. Now sometimes when you hit zoom to fit, it still won't be very readable, and that's where you can use the zoom in or zoom out buttons. Now notice that here at the start we have these inputs and outputs both being read with X values. When you have red, or as we saw previously, blue, that means something could be not right. I mean, you know, it definitely wasn't right earlier because, again, we didn't have the simulation file as a top module. But this is actually okay. The reason why we're getting red here is because if we look back at our test bench, before this first test case, we've got a 10 nanosecond delay. So that means for the first 10 nanoseconds, these outputs or these inputs are not defined. And if you have undefined inputs, the output's also going to be undefined. You know, that's one thing, you know, I didn't actually say earlier, but you can see here that in your test cases, you only have inputs. Okay, you never put an output as a test case. Because what we're doing is we're putting the various inputs that we could possibly have and seeing if it gives us the right output by looking at this timing diagram. Okay? Alright, so we can just step through this now. See, everywhere you click, it will put the cursor, and here it will give you the values of the inputs and the outputs. So when all the inputs are 0, we're getting a 1 out, which agrees with our truth table. 0, 0, 1 is giving us a 1 out, which is good. 0, 1, 0 is giving us a 0 out, which is good. 0, 1, 1 is giving us a 1 out, which is good. 1, 0, 0 is giving us a 0 out, which is good. 1, 0, 1 is 0 out like it should be. 1, 1, 0 is 0 out like it should be. And then 1, 1, 1, all 1s at the input gives us 1 out, which is right. And then it just cycles. It just goes back to all zeros. So we have a good simulation. So the next thing to do is to look at our elaborated design schematic to see if our circuit that was modeled with Verilog agrees with what we intended. You know, those 3 gates that we looked at earlier. But before we look at that schematic, let me just point out a few other things on the simulation that sometimes is handy. If you hit this gear symbol, there's this radix where you can change bases. Now in this particular design, there's no reason, you know, we just want to look at the inputs and outputs as binary, but you'll see in future labs that changing the base can sometimes be helpful. Also, there's this colors where you can change the colors of the signals and also the background. So this is handy, especially if you want to print something out. You know, you can make the background white so you don't waste printer ink. Okay, so that's something that can be useful. Also, you can move these signals around. Well, before I show you that, let me show you this feature where if you right-click on, you know, one of these variables that's in our timing diagram and come down to New Divider, you can use dividers just to organize things. So like if we just want to put the outputs on one side, see, that's one thing. You can move these inputs and outputs just by clicking and dragging. You know, and then like up here, we could put a divider, call it inputs. Oops. Oh, there it goes. So these dividers are nice because you can organize and just make your timing diagram more readable, you know, because now here's our inputs, here's our output. You know, in a design like this, it might not be, you know, all that more readable, but we'll get to designs where there's quite a few inputs and outputs, and then you'll have a crazy amount of inputs and outputs in CP233. So it's good to use some of these features because yeah, you'll definitely need them at some point. Okay, so let's look at the elaborated design schematic. So that's over here, this link. So this will show us the actual hardware that our Verilog code represents. And it should match or be very similar to the logic circuit. This logic circuit right here, these 3 gates. Okay, so what do we have here? Just gonna put this over here, I think. Yeah. Oops. Okay, so you can see that B and C are getting ANDed together. That's the same as B and C over here getting ANDed together. B and A are being ORed, and then this is a NOR gate. The little bubble here tells you that the output of the OR is being inverted, which is the same as a NOR. Well, that's what's a little bit different here. See, the bubble is over here by the input of this OR gate instead of at the output of this OR gate. But logically that's the same. Okay, it doesn't matter whether this bubble is here or on the other side of this line. It's the same logically. So even though it looks a little bit different, it's actually the same. And then the output of the AND, the output of the NOR are being ORed together, and that's our output Q. So our elaborated design schematic matches with the circuitry that we intended. We have a good simulation. So once those things are true, and also if you come down here, you can look at messages. We have no errors or no warnings. Okay, just info messages, which are fine. So that means we're ready to implement. Okay, so we're going to run implementation. Okay, so during implementation, that's when the software is starting to put the circuitry together to download through a Bitstream to your Basis 3 board. So actually, I forgot to show you the constraints file, but I'll show you that after it implements. Because in order to have the Bitstream, have a successful implementation, you need to have a constraints file. So once the implementation stops here, I'll back up and show you the constraints and just point out what's in that file. But you wouldn't want to run implementation, or you wouldn't be able to run an implementation if you didn't have your constraints file. If you try to run implementation without constraints, it's going to come up with the error, major error. Alright, so just give it some time here. Actually, while it's running, I can probably show you constraints. Yeah, if I go to sources, yeah, so this is your constraints file. This was already updated. I edited it ahead of time. When you look at it, all of this is going to be commented out. Okay, so in the constraints file, to make a comment, you lead the line with a number sign or a hash mark. Okay, to uncomment, you just take away that number sign. And an easy way to comment and uncomment is that you highlight, you highlight what you want to change and right click, and you see it just use this toggle line comment. So if I click that, it would comment out those lines. Okay, I don't want to do that right now because it's running the implementation and it could affect the implementation if I did. In fact, it would affect the implementation. Now, above where the switches are, there's 16 switches on the board, and you see that's what the constraints file is doing. It's mapping what you call the inputs and outputs in your design source. It's mapping those to the physical components like the switches and the LEDs that are on the board. So you have a block for switches. There's 16 switches, and each switch has an ID. This V17, V16, and W16 you can use to see what switch it is. If you look at the board, your Basis 3 board, at the bottom of each switch is this ID. So V17 is the switch to the far right. When you're looking at your board with the switches on the bottom, V17 is the switch furthest to the right, and then V16 is the switch right next to it, and then W16 is the switch right to the left of V16. So you see I made my least significant bit of my input C the furthest to the right switch, and I made my most significant bit A the furthest to the left, so it agrees with the truth table. Also, let's see, what else can I show you here? Oh, well, I guess we have to start the Bitstream here. It looks like our implementation was good. Now, we did get some warnings. Let me uncheck the, well, we'll look at that in just a minute, because I know those warnings are probably okay. So let's generate the Bitstream. All right, so now, yeah, you can see here above the switches is this clock block. We're going to use the clock signal in later labs, but you would just leave them commented out for now. But I also wanted to show you, we have an LED that we're using to represent the output, and the LEDs have these IDs just like the switches do. U16 is the LED furthest to the right. Okay, again, when you're looking at the board with the switches on the bottom, there's 16 LEDs. There's a block for the 7-segment display along with the anodes. We'll talk about what that's all about later on, also for the displays. There's buttons. You have 5 buttons. And then there's a bunch of headers that you can use for peripherals to connect to your board, but in this class we don't use the headers. You may use those in CP233. This class we're just using buttons, the 7-segment display, LEDs, and switches, along with the clock. Okay, but for this lab, it's just the switches and the LED. But also I wanted to show you the warnings down here. All errors are bad. Some warnings are bad, some are okay. I mean, most warnings are bad, but a lot of them you don't have to worry about. Like this one here, this timing mode one, I know is one we don't have to worry about. And then this one here about the no user defined clocks. Well, that's because we have this third line of the clock signal in the constraints commented out. But that's what we want. So you know, that's what's meant by a warning is, you know, the software is letting you know that, you know, hey, this isn't right, but it may be a case where for your particular design, it doesn't matter. Now, any warning that has to do with a latch, okay, L-A-T-C-H, and we're going to talk about what latches are later in the course, but if you get a warning in any of these early designs, you know, like this first one or the first, actually the first 5 or so, that's a warning you want to get rid of. You don't want any latches, okay? All right, so it looks like our Bitstream successfully completed. So this is what we're going to download to our Basis board. So to download that Bitstream, you want to open the hardware manager. Okay, and we have this link open target. Now before you click this open target link, you want to make sure that your basis board is powered on. And if your basis board is powered on, there's a red light in the upper left hand corner right by the power switch that should be lit. And also by that red light is a jumper. Okay, well, it's a header that has a blue jumper. That blue jumper should be in the USB position, which is the bottom two pins when you're looking at the board with the switches on the bottom. And then also there's another blue jumper that's on the right side, top right side of the board, again when the switches are on the bottom. And that blue jumper should be in the, or should be connecting the two inner pins. Okay, that's the JTAG, I believe. Yeah, JTAG mode. Okay, so once you have your jumpers in place and the board is powered on, then you click this open target. Okay, if the board is powered off and you hit open target, you're going to get some message, error message to the effect of, it can't find the board. Also, you could get that error message if you don't have the right cable. Okay, the USB cable that you need has to be the type that passes data along with power. Okay, it can't be the USB type of cable that you use to charge phones. Okay, because that type of cable doesn't have the data transfer ability. Okay, so then you should get this link here, program device. So we click that, and now we got to go find the Bitstream file. So let's see, you have to go to the folder where we put the project. So for mine, it's in this folder. It's this one, and I think it's under runs. Let's see, yeah, you want to hit runs and then implement, and then right here, see it ends with BIT. Okay, so that's our bit file. All right, and then we just program it. So this is transferring that bit file down to the board. And if it's successful now, as you flip the switches, it should agree with this truth table and agree with the simulation that we did earlier. So I'm looking at my board right now, and all switches down, the LED is lit like it's supposed to be. 001, it's lit. 010, it's not lit. 0011, it's lit. 100, it's not lit. 101, it's not lit. 110, it's not lit. And then all ones, it's lit. And if I go back to all zeros, it's still lit. So it's working on the board. Okay, so this is the process that you'll be using for all your labs. That, it's basically that you design and then type in your design source, and that's the Verilog code that's actually modeling the hardware. And then you need a simulation file, okay, to test out that design source. First thing is to get a successful simulation. Once your simulation's successful, look at your elaborated design schematic, make sure that looks right. And once those two things are right, you can go ahead and implement. Remember, to implement, you do have to have your constraints file, because that's what maps the inputs and outputs in your design to what's on the board, the physical components on the board. And then once you have an implementation that works, you generate the bitstream, download that to the board, and then test it on your board. So that's the process. You're bound to have problems. This first design, again, we keep it simple because we're trying to just teach you the process at this point. But usually, like most things in engineering, right? Usually when you build something, whether it's on a breadboard or whether it's coding, usually it doesn't work the first time. And if it doesn't work the first time, there's techniques that we teach you. First thing you would do is, because you'll see the more complex designs have multiple design sources. So when you have multiple design sources, you have to simulate each source by itself to make sure it's working, solo, right? Because if you have multiple design sources that are connected up into a bigger circuit, well, if one of those, what we call lower level design sources aren't working well, the higher level circuit's not going to work. So you got to make sure that all your design sources simulate correctly. And then, as you'll see, this elaborated design schematic is a good way to check if your overall design source, what we call a structural design, is correct. And if that's all right and it's still not working right, there's techniques that we can, or we will teach you to trace the signal from input to output to see where the problem first arises, so you can kind of isolate where the problem is. Okay? But as a first lab, I think this is a good place to stop.